It's an honor to have Peter Norvig with us today for the Microsoft Research AI Distinguished Lecture Series. I've known Peter as a colleague and a friend for many years through our meandering through different organizations. Over time, I knew him as a NASA chief scientist and then as a director of research at Google. It's a pleasure to have him visiting us today at Microsoft Research. Peter is director of research at Google. He was previously head of Google's core search algorithms group. And before that, I knew him for many years as NASA's senior computer scientist, where he was head of NASA Ames Computational Sciences Division. We had fun this morning in our fireside chat talking about some of those experiences, which you can catch when that comes out after it's edited. Peter received the NASA Exceptional Achievement Award in 2001. Peter is taught at the University of Southern California and at the University of California at Berkeley, from where he received a PhD in 1986, and later in 2006, the Distinguished Alumni Award. A few years back, people may recall that from a famous New York Times piece that even added to the number of students, but he co-taught an artificial intelligence class that signed up 160,000 students. And this actually was one of the conceptual launch points for what became this round of massive open online classes. It started right there with a creative concept from Peter and colleagues. Peter's publications include the books AI, A Modern Approach, many of you have grown up on, Paradigms of AI Programming, Case Studies in Common Lisp, VerbMobile, a translation system for face-to-face dialogue, and Intelligent Help Systems for Unix. Peter is a fellow of the AAAI, the ACM, the California Academy of Sciences, and the American Academy of Arts and Sciences. So, Peter, thanks so much for accepting our invitation and coming up to visit us. It's been great having you here.
Thanks, Eric. It's great to be here. Okay, so I want to start off by taking you back in time to 1945. And Vannevar Bush had this very forward-thinking way of looking at the world. He says that there's going to be new forms of encyclopedias. He didn't use the word Wikipedia, but he was onto something. Through this device that he called the Memex. And he had a design for it. Looks like this. It was a little bit too early for electronics, so this was all optical. So there's microfilm here, and there's projectors up there, and then there's a camera here, so you can add your new notes into this library. And this is basically a researcher's tool. And this is how he envisioned the future was going to be. So he got a lot of things right, some of the things not quite right. There's a famous question on Reddit that says if you could go back to that time, to Bush's time, and tell somebody what's the most amazing thing about life today, and the top-rated answer was, I have in my device a pocket that's capable of processing all the information in the world, the Memex basically, and I use it to look at pictures of cats and get in arguments with strangers. So maybe we fumbled the future, but it's here. And I wanted to just think for a minute of what this provides you, or any kind of research tool. And I think we can think of it on three levels. So one is you're not quite sure what's going on, and you want help in exploring and organizing your thoughts. And then you're starting to figure it out, and you want to be able to express your thoughts to someone else, to publish it, so that they can understand what's going on. And then you want to be able to follow the implications of those thoughts. I figured out something. I have a model of the world. What follows from that model? And the Memex is one way to do that. But we have another amazing tool that Bush didn't really foresee. And, oops, what happened to my clicker? A dialog box popped up. Let's try again. That's better. We have this tool of programming. And we have these core logs. So the exploration, so that's things like these Jupyter notebooks. Allow us just kind of mess around when we're not quite sure what's going on. And then when we're ready to publish, we can push it to GitHub, and all the world can see it. And of course, we can actually run these programs. So the programs have a much better capability than any other way we have of expressing thoughts of saying, what are the implications of this, right? So I can write a novel, I can write a book, and they're very good at expressing thoughts, but not so good at following through the implications, whereas programs are great at following through the implications, but they're not so accessible to everybody in terms of, can you understand what's going on? So let's go through the 4 words of the title as, what's the history? Well, we've come a long way. Here we have a room full of computers, and each one of these is 1 bit. Here we have a room full of computers, and the equivalent size is a terabyte. So we've come a long ways there. Here's the moth, the bug that was found in one of Grace Mary Hopper's computers. And here's the set of tools we have now. So we've invested a lot of time and energy over the last 50 or 60 years to make it harder for me as a programmer to insert bugs into my programs, right? I used to be able to pass the wrong type to a function, and C wouldn't complain about it, and it would just crash. Now the compiler warns me. So that's as. Now, who's we? Well, we start out with the first programmer ever, Ada Lovelace. We get a couple of pioneers, and then we expand off, and it becomes an industry. And a lot of these people did their work on their own, but we quickly learned how to have very large teams in kind of a factory setting, working together on much larger projects. So an engineering solution that goes well beyond anything we had before. We can do that with programs in a way that we couldn't do with other things. We don't have processes set up for 200 people to collaborate on writing a novel, but we can do it. You guys do it very well in writing operating systems and office tools and everything else. So we got into that stage, and we're trying to get to the stage where we have CS for all or coding for all, and there's very initiatives for that, so can everybody in the world do it? But we're not there yet. We haven't made a system that's accessible to everybody yet, and we want to try to get there. So I'm going to talk about some ways of saying, what could get us there? Is it just that the programming languages have to be a little bit better, or do we need a new way of thinking about things? So what about programming? Well, we started off here. Here's some Fortran programs. Now we have these integrated environments, and they do a much better job of actually telling you when you did something wrong. But let's think about that process. So we have a programmer. She gets an idea, organizes the thoughts, mostly on searching through Stack Overflow and putting things together, writes the program, and then you can stick the program into a computer, and now you've invented a brand new device that serves as an input-output machine, and that machine can go and do something in the real world. And that means that software is fundamentally a mathematical science. So the tools we have to express things in our programming language are basically logical, right? So we have an if statement that has a Boolean if-then-else, and it's based on the notion of proof. We only ever prove the 10-line programs in our introductory class. We don't prove the large programs, but we prove properties of them, and we have unit tests, and we show that those are correct. And the language we have for doing that is based on Boolean logic. We have assert true and assert equals, and so on. We don't have more complex ways of talking about it. So what does that mean a programmer is? So here's a historic photo. This is Margaret Hamilton, and this is the code for the Apollo lander that she worked on. And it turns out Margaret was my boss in my very first job right out of college. So I'm glad that she's getting more fame now and that I own her Lego minifig. But what we designed a programmer as is someone who can say in every possible circumstance that Apollo computer could be in, here's the right thing to do, step by step. Here's what you have to do. If A, then this, and if B, then that. So that means we've made the programmer's job is like a micromanager who's telling you everything what to do. And you do not want to have a micromanager. So here's Darth. You screw up one thing on the space station, and he's all over you. Right? It's no fun working for him. So maybe our programs aren't having any fun. Well, let's not go get that philosophical. But maybe it's not so much fun for us either to have to go that far. So are there other ways of dealing with the world than telling the computer how to do it step by step? Well, we now have this machine learning model of the world, and the standard model goes something like this. You start out with some labeled data. I've got some images and some labels on it, and I do some deep learning with some package, and then profit. Okay, we're done. Any questions? But in reality, it's more complicated than that, right? So we've taken the programming model where the programmer does the job of saying step by step what to do, and we've replaced it to the model where the programmer is more like a teacher that says, here's some examples. I want you to duplicate and generalize from those examples. And that means we've made software no longer a mathematical science, but it's more of an empirical science or a natural science. It's like doing biology. I make some observations of the world. I have a theory of the world, and then I go out and check those theories to see if they're correct. It's probabilistic rather than logical. It's uncertain, and it's observational, right? So it's a different way of looking at the world, different set of skills necessary to be successful. But it's still the case that we can take the programs that we produce, we're producing them through a learning process now rather than writing them by hand. We can shove them into a computer, and now we've got something that can do input and output. But crucially, it can observe the world and then improve itself or update itself. And you all know what we can do with that. We can play Go, we can do self-driving cars, we can do machine translation, we can do all these amazing things. And we're starting to get a toolkit to go along with this, but we got a long ways to go, right? So for regular programming, we've got 50 or 60 years worth of tools. Here, we've only got a couple of years worth of tools. And so the process is much harder. Now, I gave you that caricature of a three-step model, but the realistic model is more complex than that. So here's the realistic model. And I won't go into details, although I get a whole lecture on any one of these 8 points, and you can ask me in the question time if you want. But the idea is that there's a lot of work done in managing data, and then there's a lot of work in, after you build the model, in deploying it, monitoring its use, and updating it, so on, and integrating it into a software product, and integrating the software product into a business need. I spent a lot of time talking to startup companies, and they look at all this and they say, yeah, okay, we've done stuff with data before, we understand that, but this is going to be the hard part, right? Because look how complicated that diagram is, and I've seen the equations, and they have partial derivative signs in it, and my math's a little bit rusty, and I'm really scared about this. So this is how they estimate the time it's going to take for each of these steps. And then, we sort of help them along, and they go and do a project. And afterwards, they say, you know what? We were exactly wrong. It's actually more like this, that the machine learning training part, that was actually pretty easy. It was the managing the data, getting the data, inputting it, cleaning it, so on. That was really the hard part. And then deploying it was the second hardest part. And the part in the middle was the easiest. So it's a big change in perception. Now, one of the things that's really interesting about this part in the middle, and one of the things I think helps make it easy, is that we have this network and it's differentiable. Meaning, if you feed in the input and you get an output you don't like, there's something wrong with it, you can measure the difference between what you get and what you wanted. You can feed that back, you can make corrections along the way, and now the whole thing has improved. And that's great, and we have great tools and processes for doing that. But the problem is, this is just one step out of the 8. And what we really want is a workflow that we can differentiate the whole thing, right? So what do I mean by that? Well, back here, these are the steps having to do with acquiring the data, figuring out what features you want, cleaning the data, and so on. And if you've got good engineers, they make good choices here. You build the system, you run it, it's great. But a year later, everything in the world has changed, and all of a sudden the choices you made here are no good anymore. And there are better choices to be made. But nothing in this system will tell you that. It'll just, performance will start to degrade. Whereas over here, if something went wrong, you could automatically correct it. You have a process to do that. We don't have that here. And if we want these tools to be usable by more end users, I think we need to put the whole process under this type of differentiable approach so that any decision you make here can be revisited. And it'd be great if it could be automatically corrected, but if not automatically corrected, at least detect it and say, we got a problem here. It used to be working fine, now it no longer is. Somebody should go look at that. Okay, so we talked about what the Memex can do, exploring and organizing your thoughts, express the thoughts, and follow the implications. And we said traditional programming is one way to do that. Machine learning is a slightly different way to do that. What else could we do? What other ways of looking at the world would be a different way that would maybe help us get at these goals? So we have this idea of data science, and there's this famous Venn diagram from Drew Conway that says data science is the intersection of these three skills. One, you got to be a little bit of a programmer, maybe not quite as professional as people that do it for a living as their main job. Two, you got to know a little bit of statistics. And three, you have to know your subject area. If you're doing biology data, you got to understand some biology. If you're doing financial, you got to understand some financial. And he's broken down all these subclasses. This is considered a danger zone. If you don't know the statistics, you can get in trouble. And maybe the more programming you know, the more trouble you get in. I don't like that this is the intersection. I wish it was more like the union, that if you had some of those skills, you could be successful. And I don't like requiring somebody to have all the skills. This diagram has also been updated by Joel Gruz, who added this fourth circle here. This really strikes home for me. This one, your thesis advisor is the one who used to know how to program but doesn't anymore. And I think Joel's also right over here, that, in retrospect, you don't have to be that much of an expert in statistics, and that, yeah, you can go wrong, but most of the time you won't. Okay. So let's take you to a non-expert. So this is Makoto Koke here with his parents, who are cucumber farmers in Japan. And I'm going to let you know a secret. He does not want to be a cucumber farmer. But somebody has to take over the family business. And they're kind of expecting him to do. So what's he going to do about that? Well, he had the idea, maybe I can automate away most of that job. And the first part he looked at was sorting the cucumbers. And he said he wasn't an expert. He didn't have that bottom of expertise in the subject matter. But he said, here's these categories. I don't even know what these letters stand for. But the idea is you got all these cucumbers, and you got to throw all the ones that look like this into a barrel that's labeled BM, and you got to put the ones that look like this into a label that's labeled S. And he said, I have a little bit of mechanical engineering skill. I can build a conveyor belt, put the cucumbers on that, and I can download TensorFlow, and I can put a camera overhead, and I think I can sort them automatically into these categories. And it turned out he could, right? Now the question is, who else can do that? And how much skill do you need to be able to do something like that? Is that something that takes a really exceptional engineer, or are we getting to a point where anybody in the world can do this kind of thing? And part of the question is, what kind of conversation do you have to have with your system in order to build something like this that works? And these are the kinds of things that I would expect to be quite reasonable to have to say, right? So I got to tell it that there's 9 classes of cucumber, and I got to give it some examples. And I might want to give it some hints to say there's electric lights, but also some daylights coming in, so pay attention to that. And so on and so on. Don't worry too much about the prickly parts. Here's some examples. You got this one wrong. Let's talk about why you got it wrong. The background doesn't matter. So the conveyor belt was gray, but if it breaks and I replace it with a brown conveyor belt, don't change everything. It's the pickles that matter, not the conveyor belt, and so on and so on. These are the kinds of things that would be quite reasonable to have as part of your discussion. But the way things are today, this is not the kind of conversation you can have. Instead, you have a conversation like this. You say, well, there should be 17 computational layers, and the learning rate should be alpha equals such and such, and the batch size, and so on and so on. And augment the training images by rotating them a little bit, and optimize my hyperparameters for me automatically, right? I don't want to have to say all that. I want those things to just happen, and I want to talk about the subject matter. And we aren't there yet. And the question is, can we get there? What is it going to take? And it looks like that most of the community is not really focused on these kinds of things. We're more focused on, can we come up with a better algorithm for doing the core part, and not all these peripheral parts about making it easier. Okay, here's another language for talking to our computers. It's probabilistic programming. Right? And I said the programming we have now is logical rather than probabilistic. And I mean that two ways. One is the conditionals we have are Boolean, if then else. The variables we have a single value. They're point values. I say x equals 0. I don't say x is drawn from a probability distribution with mean 0. I could say that, but if I said that, probability distribution would be a user-defined type and wouldn't be part of the language itself, right? Probabilistic programming languages give you those types of things built in, and they also give you the ability to work in multiple directions, right? So a regular program, I go from the input to the output only. Probabilistic program, I can say, I observe this variable, now I wonder what that other variable is, and you aren't fixed to saying one is the input and the other is the output. So there's many of these systems. This is Bayes DB. I could have done infer.net, it's another very nice system. And one way to think of this is it's like making queries to a SQL database, but that some of the fields in the database are not defined, but are done by inference. And so here it's making a query about finding satellites with uncertain data, and it can give you this results. But let's skip that and say, first of all, is that a good approach? Is this idea of saying, well, maybe some people are familiar with working with databases. Can we just make a database query, and the things that are uncertain, can we, behind the scenes, do inference over that uncertain part and just gloss over the fact that there's uncertainty? Would that be a good interface for dealing with computers? And here's an example question. Say I've got a company. I want to send out a mailing of a special offer to some of my customers. And I say, from the customer database, give me all the names and emails from everybody whose age is in this demographic and his income is over this amount. But I don't really have the age and the income in my database. Rather, I have other things that are proxies for that, and I have models automatically built that infers them. So some of them is going to get wrong. There'll be a few people on that are selected that shouldn't have been, and a few people that are missed that should not have been. But that's probably fine. The cost of not sending the email to everybody is not high. The cost of sending a couple extra emails is not high. So this would be a good way to program if that's my task. So I can infer those from examples, but let's say I want to say select the diagnosis and the treatment from the electronic medical records for this patient ID. Then I don't want to treat it like a database. I don't want to say, this is a database, there's a column for diagnosis, there's a column for treatment, there's one definitive answer in each of those columns. Tell me what that answer is, because I don't have a model that's good enough for that, and an error does really hurt me. So rather, probably what I want to do in this case is some sort of simulation, and then I want to have some summarization that says, here's the differential diagnosis, not just I'm retrieving a single value from a database, but here's all the spans of possibilities. And what doctors are usually really asking is find the set of treatments with no bad interactions such that they're an approximate cover for all the diagnoses. So I'm not sure if you have this, in which case I would prescribe this one antibiotic, or you might have something else and I'd prescribe the other antibiotic. Since I can't tell, I give you them both. That's fine, we've done that before. Now you're covered. But that's not a database operation. That's more complex. And can we come up with the right models to distinguish between these two cases and to make it understandable to the users what we're doing in each of those cases? All right, so that's a challenge. That would be one possible way to go, is try to extend database programming. Other people have thought of it as trying to extend spreadsheet programming. That's another possible way to think of it. But we have the one thing that we're really good at, which is just talking. And everybody can do that. I saw this thing was pushed at me the other day. It was an article on how to create a voice menu that your customers will love. And I didn't have to read the article, and I know the conclusion should be don't. Because nobody loves it. In fact, hardly anybody can tolerate it. Right? So we've all seen those. Press 1 if you want this, press 2 if you want that. Nobody wants that. But we have other examples where it works really great. Unfortunately, most of them are still fictional, where you can have a conversation, you can talk about anything you want, and everything works out. So we're not quite there yet. We're getting a little bit better, right? If I'm stuck to a conversation where I want to say, tell me the weather, play some songs, show me a recipe, now we can have that conversation. And picking up the words is pretty easy. We're getting much better at that. Picking up the intent for things that are more complicated than those few examples, that's still getting hard. And the thing that I think is interesting about this is that we have a possibility for another phase change in the way we do computing, right? So we went from mainframe computers to personal computers to mobile, and maybe now, are we going to conversational computing? Well, if you had asked me 5 years ago, would people want to throw away their keyboards and screens and just have a speaker that sits on their desk, I would have said, that's crazy. Why would anybody want that? But a lot of people do. So maybe we're going in that direction. And maybe we're displacing this model of programming, right? So the way we have it now, if I want something to happen, I press one of these icons, and now I've given over control of my phone to the company that created that app. And there's a place to get lots of these. There's some weaknesses of this model. One is because I've given over control, I have to decide what do I want to give. And when the app is installed, there's this long list, and nobody understands them, and they just press OK. And if it acts kind of flaky, then they delete it later, right? But we can do a much better job, presumably, of privacy and security and fairness, but we aren't there yet. So one possibility is push that, do a better job of security for the apps. The other is to say, maybe we shouldn't hand control over to the app writer. Maybe we should keep control with the conversational agent. And so we have this kind of a model where we say, hi, how can I help you? And I say something, I want a pizza or I want a car to appear. And then it goes off and talks to these other services and arranges it for me. And I feel safer because I'm talking to my agent rather than talking to some app that I haven't got verified. And it's my agent's job to protect my privacy. So maybe that will work. But the systems we have for building them, and this is true for all the major vendors of these types of products, still looks much more like those terrible phone menus than it looks like having a real conversation, right? So there are application developer kits where I can say, what triggers do I want to respond to? And if I do, what dialogue do I want to output? And then when I get a response, how do I want to respond to that? So it's very much like following these menus and not like having a real model of how conversation works. There are intermediate steps we could take, right? So maybe instead of talking directly to these apps, I want to have intermediaries, right? So I might have, this is an intermediary for all the ride-hailing services, and this is an intermediary for all the restaurants. And if I trust them, then I can talk to them, and they can specialize that kind of sub-conversation. It's not quite clear yet how this is all going to work out, right? Where's the responsibility going to be split? If I'm not giving up control of my whole phone to somebody else, I'm keeping part of it. Who does which part? Okay. And we've made these things really hard to do. And so here's an example. On my phone, it used to be that on the maps, there was a little scale bar down at the bottom that was displayed all the time. And I noticed that went away sometime. And I wanted to get it back. So I did a little research, and I found out that I could, in fact, get it back. And all I had to do was look for it on Google and then Stack Overflow, and then figure out how to root my phone, and then install 200 lines of Java and 20 lines of config file, and I would have that thing right back again, right? So I could have done that, but I didn't, because I thought that would have been pretty brittle. What I really wanted to do was say, hey, Google, put the scale bar back on the map, right? But I can't do that now. It doesn't let me do it. And I find many times that part of the problem is that so much of what we do in programming doesn't make it into the program. So I've seen lots of cases where we have design documents, and you read these documents and they say, what a great job you've done of coming up with a design. You explored many possible user interfaces. You went out and you did customer experiments, and you did A/B testing of one interface versus another, and then you made the final recommendation, which is clearly the best out of all the choices, but it's the best if you were only allowed to choose one possible choice. But for some users in some places, it wasn't the right choice. And all these other options that got thrown away, they're not part of the code base. They're in this paper document only, and I can't bring them back, right? So if we had a development environment that said all these artifacts of these experiments you do are all available and can be queried and can say, hey, can you make this interface different? I would like it to look like this. You can say, oh, yeah. 2 years ago, we did a little user experiment where we tried that out. Most users didn't like it. But if you like it, I can bring it back for you, right? So I think it'd be great if we could have everything under program control rather than having dead, non-executable documents. Okay, here's another example. On a previous trip, I was in Boston. My phone goes bing, and there's an alert that says, oh, this is great. It's got it exactly right. Return rental car to Logan Airport. It's got the right map. It's got the right place. It's got the right time. Did everything perfectly. And then it had to spoil it all by saying time of travel, 23 minutes by bicycle. In some sense, this is not too bad because I commute to work and it's about 23 minutes, so it knows that that's the right length at which I usually take a bicycle, but it did not understand what return rental car meant. And I thought about, should I file a bug report? And then I said, nobody did their job wrong, right? And so if you look at who did what, and here's a kind of a simplified version, somebody's job was to parse the email from Hertz and extract an event. An event has a location and a time and so on. And then somebody else's job was to plan a trip. And from my location to the destination at that time, they planned a pretty good trip. And then somebody else's job was to create the alert and put that up. That was all right. As long as you're considering the title of the event as just being a string, everybody's job was perfect. But if the title of the event actually meant something, then it's probably not a good idea to take a bicycle. And so the problem is that as we're dealing with these uncertain worlds and dealing with the real world on the outside, interfaces just become more complicated. And we're used to this idea of saying interfaces should be simple, right? So let's go back to the early days of the web. We had this amazing thing. You could have a form, and I could fill in my name and my email and my zip code, and that could get passed back and forth between me and the web page and a server. But the most complicated thing I had to do to verify this type of information was say, well, the email should probably have an @ in it, and the zip code should be 5 digits. And I could do that either on the server side or on the web side. That's fine. And we tried to keep these interfaces as simple as possible. And there's a famous quote from Alan Perlis that says, if you have a procedure with 10 parameters, you probably miss some. And so this design idea is keep the interfaces as small as possible, because if they get complex, nobody can deal with it. And that makes a lot of sense when you're dealing with this very concrete data of just a few entries like your zip code. But if we're trying to talk to one of these devices, then there are no bounds on what that interface should be, right? So I need the whole grammar of English, both English in general and my specific dialect, and the speech patterns, those are the same, and the background information of everything that's happened recently, and all the world knowledge of what a rental car is and what it means to return it and so on. all those have to be shared between me as a dialogue participant and my speech assistant there. And the question is, how are we going to pass them back and forth? Right? Am I going to pass everything I know? Well, one, it would take too long and the bandwidth charges would be too high. And secondly, I don't want to share everything I know because there's privacy implications. So how are we going to figure out where this gets shared? And who pushes what? Who queries? When you query, what are you allowed to see? We don't know how to express this information, and we don't know how to share it and break up those tasks. And so the problem is we're trying to take this very cloud-like or fluffy, real-world, messy situation and put it into a square hole. And sometimes it's a good fit, but most of the time it's not. Okay. Now I want to, so most of the things I've talked about have been kind of on the programming side. I want to talk about another way of talking about the world in design thinking. And I spent some time with architects. And what they do is they have their own language for exploring through possible designs. And here they're trying to build a building that's going to be on this intersection here and it's going to meet certain requirements for what the building has to do. And they go through all these possible sketches. And they have kind of design patterns for how buildings should be built, and they explore those possibilities. Here's another example where they said, let's start out with this design, then say, well, we want it to be more varied, and we want to fill in the various functions that happen in different places. And now it's important to have a pass-through here. So instead of having to pass through once, we'll squish it together so you only have to pass through once. And then the way the sunlight goes, that will affect the height. And they have this whole process for generating these possibilities. And it's not in a programming language, and it's not in a conversational language. You know, if anything, it's kind of more like playing with Lego blocks. So is that the kind of tools we should provide them? Give them a bunch of Lego blocks and then have an overhead camera that's tracking what they're doing. Would that be a good way for them to express the knowledge they know? They also go and draw diagrams, but that takes a lot of work. So can we automate that process of drawing those diagrams? And then can we get to the points of implication, right? So I talked about understanding what you're talking about, publishing what you're talking about, but then there's also drawing the implications. And can we build a system where we say, here's the constraints, here's the kinds of things I know about this building, now go ahead and automatically generate a dozen possibilities given those constraints. And now I can say, oh yeah, I think number 4 and number 7 look pretty good, and number 10 and 11 will never work. Now generate another dozen given that feedback and have that kind of iterative process, right? So I think that's the kind of way that an architect would like to interact with a system. And can we come up with a language to do that? Okay, so I was trying to go through the words of the title as we made the program, and there's one word left over, and that's the word may, which talks about possibilities, preferences, utilities, desires, needs, wants, right? So these are the things we have to be able to express to our programs. If our programs are built on machine learning and they're built on optimizing something, then we have to tell our programs what we want, what we really, really want. And we have a tradition and a set of fables that talk about problems in doing this. So here's poor King Midas. He was asked for a software specification of what he wanted, and he came up with, I want everything I touch to turn to gold. And then he's looking sad because he realized there was a bug in his specification and his food is turned to gold, and that's not going to work for him, right? So that's a cautionary tale. He should have done a better job of coming up with a specification. We also have the fable of the genie and the lamp. Here the genie's caught on and says you're not allowed to wish for more wishes, right? So that's one trick. But this recipient is clever. She starts off with some gambits that it's not clear where it's going. I wish that my wishes be calculated in absolute value. And the genie said, what? And then she says, now I wish for 1,000 fewer wishes. And that's why nobody likes mathematicians. Right? So there's unexpected consequences of basically of using language, right? There's one more, and so I did on the occasion of April 1st, I did this piece you can find on Medium, and this is about the classic science fiction movie Forbidden Planet. If you remember that movie, the space explorers go to an alien planet. Everybody on the planet is dead. They have to figure out what happened. And eventually they stumble across a data center. And in that data center, they discover that the civilization had launched overnight a new software product, which was you think whatever you want, and then it will automatically appear, right? So it's kind of like this Star Trek Earl Grey tea hot. They gave everybody at once the capability to do that. And what they didn't recognize was at night they all had nightmares and monsters came and killed them all, right? So that was a site reliability engineering fail. And you can read about it in this last tweets of the Krell. So what are the bug fixes for King Midas or the genie or this Krell civilization? Well, one, if King Midas had just said, everything will turn to gold, but I want an undo function, he would have been fine. Or if he'd done some simulations first, or if he'd done some small-scale tests before launching the whole thing. Okay, don't give everybody in the world overnight the capability to do everything. Let's do a couple of user tests first. And then once you've done the regular tests, let's do some adversarial tests. Let's bring in some red teams to try to break the system. Let's monitor and deploy it. Let's have the ability to shut down, right? So there must have been one monster that came out first. And once you got a customer report, you should have hit the shutdown or at least the rollback to the previous version. They didn't have any of that. They didn't have anybody on call, I guess. Let's specify a prompt for unsafe actions. Do you really want to conjure monsters from the id? Yes or no? And have a process of continued evolution and improvement. And then I think a big part of it is don't over-rely on language, right? So all these things, the idea is you can't trust a single sentence of language. You say what you want, and the genie interprets it the wrong way, and you don't get what you really wanted. But, and we have ways of dealing with that, right? So we write laws and regulations, but we know that just those sentences aren't quite enough. So we also have case law, where we say, here's an example of what we meant when we wrote that law. And I think often we can do better by relying on cases rather than relying on just language. Okay, so we're close to wrapping up. So I said, I don't like traditional programming where you're a micromanager and you're telling the computer what to do step by step. So what are the possibilities? Well, the Memex user is a researcher. The machine learning person is a teacher. We may think it's more like a leader or a philosopher or a poet. So here's a great example of a leader. General Patton said, don't tell people how to do things, tell them what to do, and let them surprise you with the result. Right? So what he meant is say, go capture that hill. Don't say, oh, we'll take 2 platoons up this side and 3 platoons up the other side, because the people on the ground are going to know better than the general is what's the right thing to do. So let them do the right thing and surprise you. And so that's a perfect model for a machine learning approach. Don't constrain the system. You have to do it one way. Just say, this is my objective. And if we're going to have that objective, then we got to be clear about what is it that we really, really want. So let's go to 2 other philosopher poets. And of course, Mick is most famous for his statement on what we want. Can't always get what you want, but you get what you need. But I think Mick got it exactly backwards. And I would rather go with Bobby here, our Nobel laureate, who has a less famous statement with the opposite conclusion. Because these are the things that we need. But we've built an exquisite large system for measuring what we want with every click. And these are the things we said we want. And therefore, that's what we get. And it's not bad enough that I go and spend a couple hours playing Angry Bird, and then I say, oh man, that was stupid. I wish I had those hours back. It's too late for me unless I invent a time machine. But what's worse is now it's too late for all of you as well, because every one of my clicks was a vote, it gets recommended to you, and then you do it, and it's a vote to somebody else, and it's a virus that spreads and spreads. And it's more of the short term, this is what I want, and none of it feeds back into what I need, because that's the way the marketplace works. And so no matter what we can do in building better languages and building more secure and fair systems, we've got to have a marketplace that's aligned with giving us what we want. Now, there is some good news, right? So not doomed to have this always fail. There's this famous work on the tragedy of the commons, and some people have a pessimistic conclusion that means if there's a shared resource, we're always going to screw it up. But Elinor Ostrom got the Nobel Prize for saying, you know what, in reality, it doesn't really work that way. That societies going back hundreds of years have figured out how to use these shared resources. And there's a list of design patterns there, and you can look those up, of how we can go and set up our systems to make them more reliable, to do a better job of sharing what we have among everybody and helping out the community as a whole within the marketplace. So why don't I stop there, and we can open it up for questions.
Thanks, Peter. Fabulous perspective. Sumit, you have a question right away here.
So you talked about different forms of programming and how can we improve each of them. Do you also see some of these things coming together, like traditional programming, ML model building, conversation, design thinking?
Yeah, so certainly they can complement each other. I think they have a lot to say to each other, and you're starting to see a lot of things now where machine learning is being used to optimize traditional programs. So we've been working with David Patterson, who says, when I'm building an operating system, I have all these parameters. What should the block size be? And he does this similar kind of design document where he finds the optimal value, but that might change over time. So now we're thinking maybe that should all be done with machine learning to say, in this particular case, in this implementation, what's the right value for these parameters? Let's compute that rather than make the programmer specify it. So I think there's a lot of room for interaction of that kind.
I've never seen a stunned room full of MSR people before and others. Yeah, go ahead.
Before we work on something like taking the scale bar and putting it back on the map, in terms of the specification of what the user wants, don't we need to work on the composability of the widgets?
Yeah.
How do I know that when I put the scale bar back, it won't clobber the rest of the UI?
Right. And so I think that's exactly why we don't have these infinite number of possibilities, right? Because it's one thing to say scale bar on or off. There's two possibilities there. Sure, let's give them both. But if there's 20 different objects, we don't have time to test 2 to the 20th of them. So we need more like a constraint language to say, if I were to add this one more thing, how would everything else change? And that has to be specified well enough so that you don't have to test them all ahead of time, but it works. And I guess part of it is, if it's screwed up, then give the user a way to recover. So I know that we found this at Google, and I think a lot of other people have. You see a progression of having fewer and fewer types of customization. And I think a lot of that is because users make bad choices, and then they blame us, right? So we used to have this thing that says, how many results do you want per page? And everybody said, 100. That's the biggest number. And so they set their personal settings to 100 results per page, and then they started saying, oh man, Google's so much slower than it used to be. I'm not going to use it anymore because it's too slow, right? And so we either have to have some kind of warning or have to say, you know what, if you're worried about slowness, I can fix that. I can set it back to 10 results per page, and it's going to get faster again. So we need these different settings need some way to interact with each other and communicate about what they're doing.
Yeah. Hey, Andy.
Sure, just to build.
Andy first.
Okay.
What do you think are underinvested sub-areas of AI right now that we as a field ought to be investing in?
Wow. Underinvested areas of AI. So a lot of things. I mentioned like the fairness and so on. That seems really important, kind of having a better understanding of where your data comes from and what you can do with it. I'm really continue to hope that robotics is going to break through, that it kind of feels like we are now with robotics where we were with personal computers somewhere in the 1970s, where you could buy a kit and it was really interesting to play with but didn't really do anything useful. But then by a decade later, everybody had one in their home. And so I think we're at a similar place now where you can buy a vacuum cleaner robot, but it can't do much else. And hopefully we're going to get better at that. And then I'm tracking with great interest how these conversational systems work. Do we really want to communicate by voice rather than communicate by screen and keyboard? And if so, how will the programming of that play out? I think that's really interesting.
Yeah, you spoke of programming, but in more general terms, computing is assuming more and more complexity and taking on more and more tasks. And this comment about user control and setting. So, in the long run, what do you see the role of computing in people's lives? Like, how expansive should this become, and what should it do for the human society in general?
Yeah. So what should the role of programming be? And I guess there's two parts to that. What should the role of somebody else's programming be on me? So what tools that were built by somebody can I use? And we've certainly seen a lot of those. I think I'm excited about the possibilities coming up in areas like health. I think we could do a better job in these research type areas of helping people understand things. When you start looking at how many people are advocates of the flat earth theory, you sort of think, can't we do a little bit better job of helping people understand the world better? So that's one aspect of programming is how can one programmer help someone else? And then the other aspect is how much should everybody be a programmer and what can they do for themselves? How much can I say, I want to build something that's just for me. I can't expect somebody else to provide it for me, but it's for my own use. And both in terms of having a finished product that I want, and also just the process of dealing with it will help me think about things, help me model the world, help me understand it better. And I think a lot of people are missing out on that most of us in this room have that capability to do that. We find something interesting, we can explore it, we can get an answer, but most people don't have that capability. And if we could give that to them, maybe not in a traditional programming language, but something that's accessible to them, it would help them open up their world.
I think Gonzo has a question back to Gonzo.
Yeah, thank you for providing so many perspectives about different ways of programming. I was especially delighted when you mentioned design thinking, and I wanted to know your opinion. What do you think makes ML and AI special in terms of a design material, and how that impacts the way designers now think? What is so different about it from everything else that they had to interact with before?
Yeah. So the question was, what makes machine learning and AI different as a material for thinking? One of the conversations I had this morning was with someone who was saying, I built this game playing program and it started playing better than me. And that was a life-changing moment that I could see that something that I created could surpass me. And I think that happens more often in machine learning and AI than it does in other places. So certainly, I could have programmed something that would multiply 10-digit numbers a lot better than I could, but that's not a life-changing moment for me. It's these other things where you say, wow, this is really understanding something at a deep level. How did it do that? Can I understand how that happened? I think that's what's different about AI.
Over here, and then Sergi. Yeah.
What do you see as the biggest impact for quantum AI in the future?
For quantum AI? Yeah, that's a great question. Up to a couple of years ago, I was hoping that I was old enough that I would get to die before I had to worry about quantum. And so I wouldn't have to understand anything about it. Now I'm not so sure. And not just because my health is looking good, but looks like quantum's might be getting somewhere. The quantum guys at Google have, for the last 2 years, have promised me this is the year for quantum supremacy, and they haven't delivered yet. But maybe they're getting close.
Sounds familiar, doesn't it?
Yeah. I think a lot of the things that I want to do would not be helped that much, right? So a lot of things I want to do is, here's 1 trillion web pages. I want to do a small amount of computation on each one, and then I want to sum that up. So for that kind of thing, it's I/O and pushing things through, and having a quantum computer is not going to contribute to that. If I have a neural net with 1 million parameters, it's probably not going to help on that either. But if I can get a smaller number of parameters, and if the algorithms get better, I can see a potential future where we can optimize those parameters much better using a quantum computer than what we can do now. And we're not there yet, but I think that's a possibility sometime, maybe in my lifetime.
Okay, Sergi.
So we talked about different programming paradigm, and one aspect of programming is debugability. And particularly, you were answering a question there about putting it in the OS or in some critical components of the software infrastructure. The debugability becomes even more important. So I want to have your reflections on the current state, and you feel, because that's something at least we old systems people worry about.
Yeah. Okay, so the question was about debugability, and there's a lot of words that go into that. There's big emphasis now on explainable AI. People talk about transparency and trust. So these are all related in some way. So I said it's with traditional programs, we like the story that we could prove them correct. For complex ones, we never quite get there, but we can do more and more. And there's more things that we can prove. We can, even if we can't prove the whole program correct, we can often prove properties of programs. With machine learning, we've taken a step backwards with respect to that. It's harder to prove something. And some of that is because of the machine learning algorithm itself makes it harder to come up with a proof. And some of it is because the domains we're dealing with are not amenable to proof, right? So if
also the drift in data, and with that.
So let me make one point, and I'll get back to that. Right, so if I have a program that I say, this program's capable of sorting a list of numbers, I could see how I could prove that program correct. But if I have a program that says, you're going to give me a web query and I'm going to sort the web pages by rank order, there is no correct answer for that. And that has nothing to do with whether I used a neural net to do it. It just has to do with that the problem has no proof. So we have to be able to deal with that. Now, people in control theory have already been dealing with this type of problem, where they say, we're going to build a controller, and what they really like to do is say, we're only going to allow a linear controller because then we have lots of nice proofs. Of course, they're only proving the model is correct. They aren't proving that the thing in the physical world is correct. But if the model corresponds to the physical world, then they have some nice proofs. As soon as their models get nonlinear, then they give up on the proofs, but they start talking about kind of envelopes of, I think the system will stay within these types of boundaries. And so I think that's the kind of approach we should take for machine learning. We should say, I can't guarantee everything about the results, but it's going to stay here, with 1 minus epsilon probability, it's going to be within this type of envelope. And I think we need more of that. And then we just need better testing in general, right? So I think we're already in software at a point where most of what we rely on is testing rather than proof. And we just may need some better test regimes. Now, there is a big issue, right? So you mentioned this issue of online data and continual updating, right? As we were talking with Eric earlier, that it used to be you guys once a year stamped a golden CD and put it into a cardboard box and
Office 77, I think, right?
and called up some trucks to take them over to stores. That was so quaint when we used to do that, right? And So you could invest an awful lot into testing that if you only had to test once a year before you shipped it. Then we got to the point where we have web services where they're being updated every day, and you can't do the same type of testing every day. So you have to have tiered testing. We're going to do a lot of tests first, and then we're going to have the monthly test and the weekly test and the daily test. And now with online learning, we have the second-by-second test of every new data point that comes in. We do a little gradient descent, and we change our parameters a little bit. We can't run all the tests every millisecond, so we have to have even more of this tiered approach. And maybe we need more types of alerts of saying, well, things are different now today than they were yesterday. And then some filters of that, of saying, well, it's fine because today's Christmas, so we expect it to be different than yesterday, and so on and so on. Yeah.
Let's take one more question. I think Adam, and then people can come up and just meet Peter directly and have a chat. So,
sure. So you spoke about the potential for conversational systems. And I'm curious because if I'm typing in Jupyter notebooks, or even if I'm clicking icons on a GUI, in some sense I'm having a conversation with the computer. So I guess my question is, how far along the spectrum do we have to get before we start to see the benefits of CS for all? Do we have to get all the way up to like the colloquial sort of natural conversation, or is there somewhere in between?
Yeah. I think we should use the right thing at the right time, right? So everybody has their natural language, whether it's English or Spanish or whatever it is. But for lots of the things we want to do, we also have specialized language. And we have programming languages. If I want to play music, I don't use English words, I use music notation. And I think we'll see more of that, of saying, here's a task you want to do, here's a specialized way of doing that interaction. Some of it will be natural language, some of it will be the notation you're used to. Maybe you'll have to learn a few programming type concepts. And I think the future will be specialized solutions like that for particular tasks. And then the generalized part will be more just the training, this idea, right? So, I don't really like this phrase of programming or coding for everybody. I would rather have it be something like model building or problem solving for everybody. And that programming is one way to express models and solve problems, but there are other ways as well. And just this idea that you can create a model, you can debug it, you can see the results and the implications, that's what's important. And whether it's in JavaScript or Python or something else, I think is less important.
I want to thank you very much, Peter.